Okay, so let's continue with our discussion. So what we have just shown in the previous lecture is that if you start with any variety y and you take an affine variety x, then there is a bijection between the set of morphisms from y to x and the k algebra homomorphisms from the ring of affine functions, ring of polynomials on x to the regular functions on y, and this map is just the map induced by pullback of regular functions. Okay, so we are just saying that morphisms into an affine via the pullback of regular functions correspond to k algebra homomorphisms from the ring of functions on the affine. Okay, so let me repeat that: morphisms into an affine correspond via the pullback of regular functions to k algebra homomorphisms of polynomials or regular functions on the affine. Okay, fine. So now that we have this done, let me tell you that there is a little bit more to this proof that can be extracted. A nice little lemma. Here is a lemma: if y is any variety, in our case that means either affine or quasi affine variety, and x is an affine variety, say x is in An, okay, then a set theoretic map psi from y to x is a morphism. It's a morphism of varieties. If and only if y followed by ti is a regular function on y for every coordinate function ti on An. Okay, so actually this is a very beautiful statement. It tells you how to quickly verify that a set set theoretic map is a morphism, okay. And so all it's saying is that, you know, from any variety which may be affine or not affine, if you have a set theoretic map into an affine variety, to check that it is a morphism of varieties, all you have to do is you compose it with the projections which are the coordinate projections. The target variety is sitting inside some affine variety. On that affine variety you have the projections giving you the various coordinate functions. You compose this map with those projections, the resulting functions will be functions from y to k, and all you have to verify is that these are they are regular functions on y. So it's a very beautiful statement. It says a map from any variety into an affine variety, a set theoretic map, is a morphism if and only if it pulls back every coordinate function to a regular function. That's what it says, okay. And this is the proof is actually, the proof is already contained in the earlier proof that I gave you, okay. In the proof of the statement that the morphisms into an affine variety correspond to k-algebra homomorphisms from the ring of polynomial functions on that affine variety. Nevertheless, let me repeat it, okay. So you see, if, and mind you, this is an if and only if condition. One way the proof is very, very simple. If psi is a morphism, then of course since ti restricted to x are regular functions on x, it is clear, it follows that ti circle y, I am sorry, I think it should have been ti circle psi, not ti circle y, okay. That's wrong notation. Ti circle y doesn't make any sense, okay. I should compose ti with psi, okay, please correct that, okay. So ti circle psi will of course be a regular function on y. This is very simple. That's just because of the definition of a morphism, because a morphism is supposed to pull back regular functions to regular functions, okay. So the coordinate functions on an, if I restrict them to x, they are going to be regular functions on x, because after all the coordinate functions on an are the polynomials, these are the polynomial variables, okay. So when I say coordinate function ti on an, it means that I am thinking of the functions on an to be given by the polynomial ring in the n variables t1 through tn, okay. So each ti is a polynomial, okay, and you know polynomial functions are of course regular functions, and therefore if you restrict each of these polynomials to x, they are in Ox, and mind you Ox is the same as Ax, Ox is the same as Ax because x is affine, okay. And psi is already given to be a morphism, so it will pull back regular functions to regular functions. And what is the pullback of ti restricted to x under psi? It is just ti circle psi, okay, it is just the composition, and that is supposed to be a regular function on y because of the definition of a morphism, okay. So one way is very easy, it is the other way that we need to understand. Conversely, let ti circle psi, if you want, of course here when I say ti circle psi I mean ti restricted to x, circle psi it does not matter, but that is what it means, because I am evaluating ti on the image of psi which is x, because psi goes into x, okay. Conversely, assume that psi is just a set theoretic map with this property that it pulls back coordinate functions on the target affine variety into regular functions, okay. That is, this ti circle psi is in Oy for all I, okay. Suppose this holds, then I will have to show that psi is a morphism, okay. Now how do I show that psi is a morphism? I have to check two properties of psi, namely the first thing I have to check is that psi is I will have to check that it is a continuous. Then the other thing I have to check is that it pulls back regular functions to regular functions. So the idea is very, very simple. So let me tell you the idea in a very qualitative way. How do I check psi is continuous? I check psi is continuous by checking that the inverse image of closed sets are closed. But what's a closed set? A closed set on X is just given by common 0 locus of a bunch of polynomials, okay. And what is the inverse image of such a set under psi? It is the common 0 locus of the bunch of regular functions on Y that I got from these polynomials by composing with psi, and the set of common zeros of a bunch of regular functions is a closed subset of a variety. Therefore psi pulls back over closed sets to closed sets, so psi is continuous. It's very simple. So let me write that down. So you know it's actually this argument. It's actually just this argument, but let me write it here. If Z of j in X is a closed subset, then psi inverse of Z of j is so I'm just reproducing what I've written there. It's psi inverse of Z of j is the intersection of Z of H where H belongs to j, and this is the intersection H belongs to j of Z of H circle psi, which is closed in X. Okay, the 0 set of a single regular function is a closed subset, okay, and an arbitrary intersection of closed sets is again closed subset. Therefore this is a closed set. So what I have proved is that the inverse image under psi of a closed set is a closed set. So this implies that psi is continuous. Okay, now the only other property that I have to check in order to ensure that psi is a morphism is that it pulls back regular functions to regular functions. So now there's a small hitch here in my argument. I have already used the fact that H circle psi is a regular function, which is something that I will have to show, okay, and that's purely a matter of verification. So let me do the following thing. So the correct way to do it is to use the fact that these are regular functions. Yeah, so basically it's a calculation. So what I need to do is the following. So let me rub this off just to say it in sequence. So I need to tell that start with, so I have to make a small calculation, start with an element H in start with an element H in AX. H is just a polynomial in T1 through Tn restricted to X. This is what it means, because X is an affine variety in An, and the ambient affine space An in which X sits is supposed to have these as coordinates. So the polynomial ring generated by this is a set of all polynomial functions on the affine space in which X sits, and any element in the polynomial function set in the ring of polynomial functions on X is the restriction of a polynomial to X, okay. But of course the function is uniquely defined, but the polynomial is not uniquely defined. It is defined only up to addition by an element of the ideal of X, okay. So choose H instead of H, choose a polynomial, okay, that represents H, and call that also as H, okay. Then say H is, if you want, let me call this as G bar, where G is G of T1 etc. Tn. G bar is the image of G in Ax, which is a quotient of the polynomial ring in n variables, in these n variables, okay, which is the ring of all polynomial functions on A. Okay. Now look at so I want to calculate what the pullback of H under psi is. This is what I want to do. Okay. So what is H circle psi? What is H circle psi? Let's calculate this. So basically what's happening is that I have y, I have psi, I have x, and here I have a polynomial h, okay, and this is my map H circle psi. Okay, it is just pullback of H under psi. It is just psi star of H. Okay, it is just this. What is it if I evaluate it? So if you take a point small y in capital Y, that goes under psi to psi of y, and that will go under H, and you know the psi of y will have some coordinates, lambda 1 etc. lambda n, okay, and that if I apply the function h, of course the function h is going into k, which is a1 if you want, okay, with the Zariski topology, alright. So if I apply h, applying h is the same as applying g, okay. So what I will get here is g of lambda 1 etc. lambda n. This is what the map, this is this map which is H circle psi, okay. And if you look at it now, it will be clear that H circle psi is a regular function on is certainly a regular function on capital Y, because it is actually a polynomial in the Ti circle size in exactly the way in which G is a polynomial in the lambdas in the T's. See, G is G of T1 etc. Tn, okay. So if you calculate H circle psi, it will be actually just G of T1 circle psi etc. Tn circle psi. You will get this, because you know evaluate it and check. Since H circle psi, if I evaluate it at a point, what will I get? I will get H of psi of y, and H of psi of y is lambda 1 through lambda n, and then I evaluate H on that. H is represented by a polynomial g, so I will get g of lambda 1 etc. lambda n, okay. And you will also see that g of T1 circle psi etc. Tn circle psi evaluated at the point y is just evaluating g on T1 circle psi of y comma dot 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 Tn circle psi of y, but then you see psi of y is the point lambda 1 through lambda n, and if I apply Ti to that I will get lambda I, so I will simply get g of lambda 1 etc. lambda n, okay. So this calculation tells you that H circle psi is just a polynomial in the Ti circle psi. So what is H circle psi? It is a polynomial combination, it is a polynomial in these functions. But what are these functions? They are already given to be regular functions on y. Each Ti circle psi is already a regular function on y, and so if you give me a bunch of regular functions on y and write a polynomial in those regular functions on y with coefficients in the field, the result is again a regular function, because sum and product of regular functions is again regular function, okay. So it's so all this will tell you that H circle psi is in O y, okay, since each Ti circle psi is in O y. you will get this. So what this will tell you in principle, it will tell you that psi pulls back regular functions on x to regular functions on y. Okay, so this is one of the conditions for the map psi to be a morphism. The only other condition now I have to check is the continuity of psi, which will follow as I gave in the earlier proof. So only I have to check psi is continuous, and that's because of the following thing: psi is continuous because psi inverse of z of j is psi inverse of intersection of z of h, or let me put z of g. G belongs to j. This is intersection g belongs to j, z of g circle psi, which is closed in y. So I am using the fact that if you give me a bunch of regular functions and look at the set of common zeros, that's a closed, that gives a closed locus, and the reason for that is every regular function is locally quotient of polynomials, and looking at the zero set is actually the same as looking at the zero set of the numerator polynomial. Okay, so and we are done. So you verified that if psi pulls back coordinate functions to regular functions, then not only is psi pulls back any regular function to a regular function, but it is also continuous, so psi isomorphism. Okay, so it's a very beautiful statement. It tells you very quickly how to verify that a map from in a given variety into an affine variety is a morphism. Okay, it's very simple. All you do is you just show that the pullbacks of all the coordinate functions are regular functions. That's all you have to check. Okay, fine. So this is a fact that is kind of buried in the proof of the theorem that I gave in the previous lecture, so I just wanted to bring it out. Now what we will do is let's try to apply this and reconcile some of the results that we had that we have already talked about earlier. So if you recall that if you have f in polynomial ring k1 etc. up to k of x1 through xn, then then we have the bijection, the following bijection. So you see you have an and this is just this is with this here is with coordinates x1 through xn. Okay, and you had df, the affine open, the basic affine open set defined by f. This is just it's just the complement of the zero set of f. It is an minus zero set of f. Okay, so it is a locus where f does not vanish, and that is an open subset. And I told you that this is a basic open subset. It is basic because every open subset can be written as union of such open subsets, and because of quasi compactness, in fact it can be written as a finite union of such basic open sets. And I told you that this, the other beautiful thing about this subsets of this type is that they are actually themselves isomorphic to affine varieties, and I told you that they are isomorphic to a closed, irreducible closed subvariety of an affine space one dimension more. Okay, so how does that come about? That comes about by taking an plus 1 of k with coordinates the same x1 through xn, but I add an extra coordinate y. Okay, and what I do is, well, I look at the zero set of y f minus 1, okay. So f is a polynomial in the first n variables, and y times f becomes y minus 1 becomes a polynomial all the n plus 1 variables, okay, and this polynomial is irreducible, and its zero set therefore gives an irreducible closed subset of affine space. Mind you, this is open and this is irreducibly closed. Of course you must remember that this being an open non-empty open subset of affine space, of course I am assuming this is a non-empty set, okay. F is a non-constant polynomial, okay, and mind you that that is an open subset of affine space. Non-empty open subset means that it is also irreducible and it is also dense, mind you. This set here is irreducible and dense, okay, and this set here is irreducible and closed, and we have this projection. You project onto first n coordinates, that is this projection map, okay, and under this projection map you have an isomorphism under the projection. There is a bijective map from here to here. This is something that I told you, and in fact I told you that this bijective map is actually an isomorphism of varieties, okay. In fact the map is very simply defined. You give me an element lambda 1 etc lambda n at which is here, which means f does not vanish at this element. You simply associate to it the this element lambda 1 through lambda n, and then you add 1 by f of lambda 1 through lambda n. Then you know this satisfies the last coordinate y multiplied by f applied to the first n coordinates minus 1 equal to 0, so it satisfies this equation, and I can invert f of lambda 1 through lambda n because lambda 1 through lambda n is in the locus where f does not vanish, okay. So I told this it's very easy to check that this is a bijective map, but I told you actually to check as an exercise that it's a homeomorphism of topological spaces. I hope you have done that, but now the time, and then I told you that it's even an isomorphism of varieties. I told you that this is an isomorphism of varieties, and you know I told you that this is something that we will see later, because when I told you at that time I had not defined what a morphism of varieties was, but now that I have defined what a morphism of varieties is I can go back and justify this statement, okay. So if you look at this statement now, okay, what you can see immediately is that this is a quasi-affine variety because this is an open subset, non-empty open subset of an affine variety, and this is an affine variety, okay. And if you take this map, I have a set theoretic map now. It's even a bijective map. I have a set theoretic map from here to here, okay, and let me take the map in this direction, okay. Let me take the map in this direction. It is a bijective map, okay. So you see I have a map from a variety to an affine variety. This is an affine variety, okay, and it's a set theoretic map. How do I check that it is a morphism? I check that it is a morphism by checking that if I compose it with the coordinate projections, okay, then the resulting things give me regular functions on the source variety, okay. So you see if I compose this map with the coordinate, if I compose this map with the first coordinate projection, I simply get the first coordinate projection here. If I compose this map with the second coordinate projection and so on up to the nth coordinate projection, I simply get the nth coordinate projection here, which are of course regular functions, okay, because a polynomial is always a regular function, and a regular function restricted to an open set is also a regular function, there is no problem, okay. What about projection onto the last coordinate, okay? If I project, well I mean so that's it. I mean I just check that if I project onto the last coordinate I get 1 by f, okay. If I take a point here, I take the image there and I project onto the coordinate, last coordinate, what I get is a point here going to 1 by f of that point, so I get the function 1 by f, but 1 by f is also a regular function on df, okay. So I have verified the condition that every projection of this map with the coordinate functions is a regular function, therefore this becomes a morphism. So it is a bijective morphism now. Okay, now the only thing you have to worry about is that if it's a bijective morphism, so you would be worried as I had warned in one of the earlier lectures that a bijective morphism need not be an isomorphism because the inverse map need not be a morphism. Okay, but the fact is that what this induces at the level of regular functions, okay, is the following. You will see that if I call this map as let me call this map by something, let me call this as P. No, I should not call it, this way is projection, so I should not call it projection, I should call it something. So let me give it some name, well, phi if you want. Okay, let me call this as phi sub f because this f is involved. Okay, then you know this phi sub f will induce alpha of phi sub f, which is a pullback map. It is phi sub f star, it is a pullback map. And what is this, what is a pullback map? It will go from the regular functions on the target, so it will go from a of z of yf minus 1 to the regular functions on the source. This is what you will get. Okay, this is the pullback map, this is the pullback map. And see this is this coordinate ring, the ring of functions, is given by simply k of x1 through xn comma y divided by yf minus 1. This is what it is. This is the ring of functions on that irreducible closed subset. It is just the ring of functions on the ambient affine space, which is the polynomial ring in these n+1 variables, the first n being given by the x's and the n+1th variable given by y, modulo the ideal of this closed subset. The ideal of this closed subset is the ideal generated by yf minus 1 because the yf minus 1 is an irreducible polynomial and it's an irreducible element in this polynomial ring, which is a UFD, unique factorization domain. So the ideal it generates is prime. So actually I should write here the radical of this ideal, okay, because if I take z of j, then I will have to put I of z of j, okay, but I of z of j is rad j, so I will have to put radical of yf minus 1, but radical of yf minus 1 is the ideal, radical of the ideal generated by yf minus 1 is the ideal generated by yf minus 1 because yf minus 1 is a prime ideal, and that is because yf minus 1 is an irreducible polynomial, okay, and it is sitting inside this polynomial ring which is a UFD. Okay, so this is the ring of functions, and I want you to check that this is the same as polynomial ring in n variables localized at f. Okay, so this is an exercise which I want you to do, that to check that it is very clear that if you take an element here, what is an element here in the localization, it is of the form g by f power n, where g is a polynomial in these n variables, these n x's, divided by some power of f. That is of course a regular function on df because it is a quotient of polynomials. A regular function is something that is locally a quotient of polynomials, in this case it is globally a quotient of polynomials, so it is very clear that these guys are certainly here. The fact is they are all, you can check that the inclusion of this inside that is actually a surjective map, therefore this is actually equal to that. Okay, this is this checking can be done, and now after you do that checking, you check that this map is the natural isomorphism you get in commutative algebra. It is the map that sends y to, it is a map that is given by sending xi to xi and send y to 1 by f. Okay, this map comes from this direction because of the universal property of the polynomial ring in n+1 variables, and the map comes in, and this map is an isomorphism because the map in this direction comes from the universal property of the localization. So you can check that this pullback map is actually this isomorphism which is completely commutative algebraic. Okay. So what this will tell you is that this map phi f, which is a bijective morphism, if you look at the pullback map, the pullback map gives you an isomorphism. Okay. And now you can if you believe that whenever you have this isomorphism of whenever you have an isomorphism, then you know the object I mean this tells you that it is correct to define the it is correct to think of df or dff as an affine variety, okay, and to call this as a of dff, which is what we started with. We defined a of dff like this, okay, and I had given you I had proved that if you take the whole polynomial ring, then the O of that I mean if you take the whole affine space, then the O of affine space is the same as E of affine space. I told you that holds not only for affine spaces, it holds for affine varieties, it holds for basic opens, okay, and that is this checking that you have to do. And so all this tells you that what we originally started with, namely with defining this as A of df, is the definition is correct, because we define A only for affine varieties and df is an affine variety because it is actually isomorphic to this. The fact that this bijective morphism is actually an isomorphism, namely the crucial fact that the inverse map is a morphism, comes from the fact that this is an isomorphism, okay, it comes from this fact, it is reflected in this fact that this is an isomorphism, alright. So this is justification for defining A of df as this set, as this ring, okay, that is one thing. And then the final thing that I wanted to say is about the equivalence of categories of affine varieties and finitely generated K algebras which are integral domains. So for that I need a little bit of functoriality. So here is a lemma that you can easily check. If y to x1 to x2 phi psi is a sequence of morphisms of varieties with x1 and x2 affine, okay, then the morphism, then the K algebra homomorphism K sorry A of x2 to A of y given by the pullback of psi circle phi, which is psi circle phi upper star, is the same as the composition. I should be careful here, it is ax2, I should not write ay, I should write oy, because as I told you it is a convention that we write a only if it is an affine variety, okay. Y is just a general variety, it need not be affine but only x1 and x2 are assumed to be affine. Yeah, so let me continue the statement. Given by alpha of psi circle phi is the same as the composition A of x2 to A of x1 to O of y, which is psi upper star. This is the same as alpha psi, and this is phi upper star. This is alpha of phi. So I should write it as first apply phi upper star, then apply first apply psi upper star, then apply phi upper star, which is the same as first applying alpha of phi, then apply alpha of psi. Okay, this is just functoriality. This is functoriality. I'm just actually this looks a little long to write down, but all I'm saying is that the notion of pullback of maps is very functorial, which is I mean if you have a composition of morphisms, pulling back a function on x2 all the way to y is the same as first pulling it back to x1 via psi and then further pulling back the resulting function via to y via phi. Okay, this is a very this is something that you can check very easily. Okay, there is nothing much about it. Okay, now this is a very easy lemma to check. Okay, so I leave it to you, but then the important corollary to this lemma is the following. Two affine varieties x1 and x2 are isomorphic, and when I say isomorphic it means as varieties if and only if ax1 and ax2 are isomorphic as K algebras. Okay, so this is basically because morphisms. So the proof is, it follows from the fact that morphisms of varieties from x1 to x2 via this alpha map which is pullback, is this set can be bijectively identified with morphisms of K algebras from ax2 to ax1. Mind you, here I should have put ox1, but I can replace ox1 by ax1 because x1 is affine. Okay, if x1 is not affine then I have to replace this ax1 by ox1. That is what we prove. Alright, and of course this map is as usual, you send a morphism to alpha of phi which is phi upper star. This is just a pullback. Alright, and what I want you to understand is that if this morphism phi is has an inverse, then there is a psi such that phi circle psi and psi circle phi are corresponding identity maps. Okay, and because of this lemma it will follow that phi star and psi star will be inverses of each other, and that will tell you that phi star phi is an isomorphism of varieties if and only if the induced map on pullback of regular functions phi star is an isomorphism of K algebras. Okay, so you get this corollary as a result of this lemma and the earlier theorem that morphisms into an affine variety are in bijective correspondence with K algebra homomorphisms from the polynomials on the affine variety, polynomial functions restricted on the affine variety. Okay, so so this completes the statement that we have an equivalence of categories. So let me write that down. That's the final statement, which is which, as I mentioned a couple of lectures at the end of the lecture before the last one, that it is a grand statement of the Hilbert-Nullstellensatz ansatz, namely it's an equivalence of categories. So let me write that down here. So so you have corollary we have an equivalence of categories so here is the equivalence of categories. On this side we have a category of affine varieties okay. These are the objects, and when I say category of affine varieties, it means that the objects are affine varieties, the morphisms are varieties, and on this side we have the category of affine coordinate rings over K, which should be defined as category of finitely generated K algebras that are integral domains and of course the morphisms there are K algebra homomorphisms, and you have an equivalence of categories, namely you have a functor in this direction, okay. A functor is a generalization of function, okay, but since the source and target are not sets but they are categories, we don't use the word function, we use the word functor. So you have a functor like this, which has a kind of inverse functor in this direction, okay. And what is the equivalence? You give me any x, you send it to Ax, so in this direction it is A, okay. And if you give me, and a functor is not only supposed to map objects to objects, it is also supposed to map morphisms to morphisms. So if you give me another affine variety, I get Ay, and if you give me a morphism phi from x to y, I get A of phi. This A of phi is nothing but phi star, pullback of functions, which is just alpha of phi in all our previous notations, okay. So this is a functor, for every object here you get an object there, for every object here which is an affine variety I get an object there which is a finitely generated K algebra, and that is an integral domain because it is a polynomial ring modulo a prime ideal, alright. So it is a finitely generated K algebra which is an integral domain, and given any morphism in this direction on this side I have a pullback of functions which is a K algebra homomorphism, okay. And this, and that the set of all such psi is bijective to the set of all such K algebra homomorphisms on this side is a statement that we have stated as a corollary there, okay. I mean it is part of the theorem that we proved. And what's more, what you should see is that the arrows are reversed, an arrow in this direction gives rise to an arrow in the other direction because you pull back functions from the target to the source. So we say that A is a contravariant functor because it changes the direction of the arrows as it goes. An arrow in this category is converted into an arrow in the reverse direction in the target category, so it is called a contravariant functor. And what is the inverse functor in this direction? The inverse functor in this direction is given by max spec, okay. It is given by max spec, and namely if you start with a finitely generated K algebra, if you start with a finitely generated K algebra which is K of x1 etc xn modulo some prime ideal, okay, then what you can do is that you can take max spec of that and this can be identified via the Nullstellensatz to the 0 set of P as an affine variety in A of An in An with coordinates these xi's, okay. And so if you go like this, what happens is that you get a functor in this direction. This functor is also contravariant, okay. And if you have a bijection between sets, what usually happens is that you start with an element here, you go this way, and then when you come back you should get the identity on this side, and similarly for the other side. But when you have a bijective equivalence of categories you will not get the identity, what you will get is something up to isomorphism. So if you start with something here, you take Ax, and then if you take max spec of Ax, what you will get is something that is isomorphic to X. And why you get the isomorphism is because A of that and A of your original x will be isomorphic because of the choice of coordinates. The isomorphism comes because you are choosing a bunch of coordinates. Okay, the isomorphism comes because it depends. When I write Ax, okay, you are choosing coordinates. So here is the very important subtle technical point. The technical point is the following: an affine space, if you take an affine variety, the affine variety can sit as a closed subset in any affine, in so many affine spaces. For example, take the plane. The plane can simply sit inside A2 via the identity map. It can sit as a plane, it can sit as a 2 plane in A3, it can sit as a 2 plane in any AN. But you know, if you but how is the affine coordinate ring defined? Affine coordinate ring is defined based on the embedding, based on the ambient affine space in which your affine variety is sitting. So if X is a plane sitting inside if X is the plane A2, then Ax will become the polynomial ring in 2 variables. But if X is say the xy plane sitting in 3 space, then Ax will become kxyz mod z, which is again kxy. Okay, so the beautiful thing is this affine variety, no matter in what affine space it is sitting in as a closed subvariety, the Ax that you get will always be the same up to K algebra isomorphism. Okay, that is a beautiful thing. So the coordinate ring, the ring of functions on the affine variety, is a very nice object. It does not depend on the embedding of the affine variety in a certain affine space. If it sits in some other affine space also, the ring of functions will change only up to isomorphism, which is a nice thing, which goes on to tell you that the fact that something is an affine space is a very intrinsic thing. Okay, that it tells you that trying to characterize an affine variety by its ring of functions is a very intrinsic thing, because it does not depend on the extrinsic choice of embedding, of putting that variety as an irreducible closed subset of some affine space. No matter in which affine space you put it as an irreducible closed subset, if you calculate the affine coordinate ring, you will still get the same ring up to an isomorphism, which means essentially a change of variables. Okay, so you will get an isomorphic ring. So what this tells you is that the affine coordinate ring, or the ring of polynomial functions on an affine variety, is defined up to isomorphism and depends only on the variety. It does not depend on which affine space in which you are considering this as an affine variety. Okay, so it is a very intrinsic object. So this A is a very intrinsic object for an affine variety, and that's the subtle point. So we started with this definition, then it's nice that we have come to this point where we are able to say that this does not depend on the affine space in which you are considering X as an irreducible closed subset. Okay, so with that I'll stop this image.